Welcome! In this video, we'll tackle the problem maximum number of balloons. We'll explore the challenge, break it down step by step, and review the most efficient approaches to solve it. Let's dive in and start coding. In this problem, we are tasked with determining how many times we can form the word balloon using the characters from a given string called text. Each character in text can only be used once, which means we need to calculate how many complete instances of balloon can be constructed using the available letters. The input will be a string of lowercase English letters, with a length between 1 and 10,000. The output we need to provide is an integer representing the maximum possible instances of balloon that can be formed from the input string. To better understand the problem, let's consider the first example where the input string is LeetCode. Here, we analyze the frequency of each letter required to form the word balloon. The string contains 1 B, 1 A, 2 L's, 2 O's, and 1 N. Since each instance of balloon requires exactly 1 B, 1 A, 2 L's, 2 O's, and 1 N, we can see that this string has just enough of each letter to form one complete instance of balloon. After using these letters, no additional instance can be formed, so the output for this example is 1. Now, let's look at a second example with the input string LeetCode. In this case, the string contains 2 B's, 2 A's, 4 L's, 4 O's, and 2 N's. Since forming one instance of balloon requires 1 B, 1 A, 2 L's, 2 O's, and 1 N, we can see that the available counts are sufficient to form two complete instances of balloon. After using the required letters for these two instances, there would not be enough remaining letters to form a third instance. Therefore, the output for this example is 2. To summarize, every complete instance of the word balloon requires the following: 1 occurrence of B, 1 occurrence of A, 2 occurrences of L, 2 occurrences of O, and 1 occurrence of N. In the previous example, the counts of each letter allowed us to form exactly 2 instances of balloon. Now, let's consider another example with the input string LeetCode. In the example where the input string is LeetCode, we notice that it does not contain all the necessary letters to form even one instance of balloon. Specifically, it lacks the letters B and A, which are essential. Without these letters, it's impossible to create the word balloon, so the output in this case is 0. Additionally, the problem comes with constraints such as the input length being between 1 and 10,000, and the solution must efficiently handle large inputs. It's also important to consider edge cases like an empty input string or cases where only some of the required letters are present, as these can help us ensure our solution is robust and handles all scenarios correctly. To tackle this problem, we first consider two main approaches. The brute force approach relies on generating all possible substrings of the input text and then checking how many times the word balloon can be formed. As we identify matches, we decrement the count of used characters until no more instances of balloon can be created. While this method is theoretically valid, it is extremely inefficient due to the sheer number of substrings that need to be processed. Generating substrings alone has a time complexity of O(n squared, and verifying each one adds even more overhead. This makes the brute force approach impractical for larger inputs. On the other hand, a more efficient method is the count-based frequency analysis. Here, we focus on the specific characters that make up the word balloon, B, A, L, O, and N. By counting the occurrences of these characters in the input text, we can determine how many complete instances of the word can be formed. Since the letters L and O appear twice in the word, their counts need to have to get an accurate measure. The limiting factor is the character with the smallest adjusted frequency, and this forms the basis for a more streamlined solution. This frequency-based approach is not only conceptually simpler but also computationally efficient. It requires just a single pass over the input text to count the character frequencies, which is an O(n) operation, followed by a constant amount of additional computation to determine the limiting character. With this understanding, we can now outline the steps for the optimized frequency analysis. First, we use a dictionary or hash map to count the occurrences of all characters in the input string. Next, we extract the counts for the specific characters B, A, L, O, and N, making sure to divide the counts of L and O by 2, since these letters are used twice in the word balloon. Finally, we return the minimum of these adjusted frequencies. This gives us the maximum number of times the word balloon can be formed. Here's a Python implementation that demonstrates this approach. Using the counter class from the collections module, we count the frequencies, and then simply compute the minimum of the relevant values. This compact and efficient solution directly addresses the problem requirements. The optimized frequency analysis method stands out for several compelling reasons. First, it is highly efficient, running in O(n) time and using O(1) space, which makes it ideal for processing large input strings of up to 10,000 characters. Second, its simplicity ensures that the solution is easy to understand and implement, eliminating unnecessary complexity. Finally, it is scalable, handling competitive programming constraints with ease. When we compare this to the brute force approach, the advantages are clear. While brute force might be easier to conceptualize initially, its exponential time complexity makes it unsuitable for real-world scenarios. In contrast, the optimized method leverages the structure of the problem to achieve an elegant and optimal solution. The key insight here is recognizing that the task revolves around the frequencies of specific characters, adjusted for duplicates, rather than iterating over substrings. This was the pivotal realization that allowed us to simplify the problem and focus on what truly matters. To conclude, the chosen strategy, optimized frequency analysis, is the best approach for solving this problem. It is efficient in terms of both time and space complexity, ensuring that the solution is not only fast but also memory efficient. The simplicity of its implementation makes it accessible, while its scalability allows it to handle large inputs seamlessly. By avoiding the inefficiencies of brute force methods and directly targeting the problem's constraints, this strategy delivers an optimal solution. Its design is a testament to the power of understanding a problem's structure and leveraging it to create a tailored and effective approach. To solve this problem, we need to figure out how many times we can form the word balloon using the letters provided in the input string text. The key observation is that each letter in balloon has a specific frequency. B appears once, L appears twice, O appears twice, and N appears once. To form the word, the frequency of these letters in text must meet or exceed their required counts. For example, if text is LeetCode, we can only form balloon once because we have just enough of each required letter. The goal is to determine the maximum number of complete balloon words we can form by counting the frequencies of these specific letters and comparing them to the requirements. The first step is to pre-compute these required frequencies for balloon using a dictionary or array, which will act as a reference throughout the algorithm. Next, we count the frequencies of each letter in the input string text. This can be done by iterating through text and storing the counts in a dictionary. For example, if the input is LeetCode, the resulting frequency dictionary will be N1, L2, A1, E1, B1, O2, K1. Now, to calculate how many times we can form balloon, we take each required letter, divide its frequency in text by its required frequency in balloon, and use integer division to ensure we're counting only complete words. For instance, for LeetCode, the calculations would be B appears once, so 1 divided by 1 equals 1 is L appears twice, so 2 divided by 2 equals 1, and so on. The smallest of these results is the limiting factor, which determines the maximum number of times we can form balloon. Once we've calculated the limiting factor, the result is simply the minimum value obtained from the division calculations for all required letters. This value represents the maximum number of complete balloon words that can be formed from the input string. By focusing on frequencies, we avoid the need for more complex operations like generating substrings or constructing the word directly. This approach is efficient because it uses frequency counts to determine the output in linear time, O(n), relative to the length of text. The insight here is that the letter with the smallest usable count effectively limits the output, as all the letters are required to form the word. Using dictionaries or arrays to store frequencies also ensures that the algorithm remains simple and efficient. To implement this algorithm, we use dictionaries to store the letter frequencies. The first dictionary keeps track of the counts for each letter in the input string text. For example, LeetCode would produce N1, L2, A1, E1, B1, O2, K1. The second dictionary contains the required frequencies for the letters in balloon, which are B1, A1, L2, O2, N1. This makes it easy to compare the available counts in text with the required counts in balloon. To optimize further, we can skip counting letters in text that aren't part of balloon, as they don't contribute to forming the word. Additionally, if any required letters count as 0 during the frequency check, we can immediately return 0 since it's impossible to form balloon without all the necessary letters. When applying this algorithm, we consider several edge cases to ensure correctness. If the input string is empty, as in text equals, the output is 0 since no letters are available. If there aren't enough of certain letters, like text equals ablen, the output is also 0 because the required counts for L and O aren't met. For an exact match, such as text equals balloon, the output is 1 since the input contains exactly the letters needed to form one balloon. If the input contains excess letters, like text equals balloon balloon balloon, the output is 3 because the input can form balloon 3 times. Finally, irrelevant letters in the input, such as in text equals balls ballons, don't affect the result since they are ignored during frequency counting. These examples highlight how the algorithm handles different scenarios effectively. The implementation of this algorithm is straightforward using Python. We first define the required frequencies for balloon as a dictionary, B1 of 1, L, 2, O, 2, and 1. Then, we count the letter frequencies in the input string using Python's collections counter. To calculate the maximum number of balloon words, we compute the integer division of the counts for each required letter and find the minimum result. This ensures that we consider the limiting factor. The final implementation is both concise and efficient, running in O(n) time, where n is the length of the input string. This makes it suitable for processing even large inputs quickly and accurately. This Python implementation solves LeetCode problem number 1189, maximum number of balloons. The goal is to determine how many times we can form the word balloon using the characters in the given string text. First, we use Python's counter from collections to count the frequency of each character in the input string. The counter creates a dictionary-like object where keys are characters and values are their corresponding counts. Next, we define the frequency requirements for the word balloon in the balloon_count dictionary. For example, the word balloon requires 1 B, 1 A, 2 Ls, 2 Os, and 1 N. To calculate the maximum number of times balloon can be formed, we use the formula char_count, char, / balloon_count, char, for each character in the balloon_count dictionary. This division ensures that we account for the frequency constraints of each character. For example, if there are only 3 Ls in the text, we can form at most 1 balloon since 2 Ls are needed per word. Finally, we use the min function to determine the limiting factor. The minimum value across all the required character frequencies represents the maximum number of balloon words that can be formed. This approach is efficient, with a time complexity of O(n), where n is the length of the input string, as we traverse the string once to count character frequencies and perform a constant amount of work for each character in balloon. The space complexity is O(1), since the frequency dictionary for balloon is fixed in size. This makes the solution both optimal and elegant for the problem. Here, we start by defining a method called maxNumberOfBalloons that takes a string, text, as input. The first step is to build a frequency map for the characters in the input text. We use a hash map to count how many times each character appears. This is achieved by iterating over the characters of the string, and for each character, we either increment its count in the map or initialize it to 1 if it's not already present. Next, we define another map that represents the frequency requirements for each character in the word balloon. For example, the word requires 1 B, 1 A, 2 Ls, 2 Os, and 1 N. With these two maps, the next step is to calculate the maximum number of balloon words that can be formed. We initialize a variable, maxBalloons, to the maximum possible integer value. Then, for each character needed in the word balloon, we calculate how many times it can be contributed by the input text. This is done by dividing the available count of the character by its required count, and we continuously update maxBalloons to the smallest result among all the characters. Finally, after processing all the required characters, we return the value of maxBalloons. This value represents the maximum number of complete balloon words that can be formed using the input text. If any character is missing or insufficient, maxBalloons will naturally be reduced to 0, ensuring that the method correctly handles cases where forming the word isn't possible. This implementation is efficient, as it processes the input string in linear time and performs a constant amount of work for the frequency checks, making it well suited for this problem. To solve the problem, we first count the frequencies of each character in the input string using Python's collections counter. For the input string Li-Bolko, the output of the counter gives us N1, L2, up1, E1, B1, O2. This tells us how many times each character appears in the string. Next, we define the frequency requirements for the word balloon. This word requires specific counts of characters, 1B, 1A, 2 Ls, 2 Os, and 1 N. This is represented as balloon_count equals B1, up1, L2, O2, N1. Finally, to calculate how many times the word balloon can be formed, we compute the minimum of the integer division between the available counts and the required counts for each character. The formula for this is min char_count, char, / balloon_count, char, for char and balloon_count. Now, let's calculate this step by step for each character in balloon_count. For B, we take char_count, B, / balloon_count, B, which is 1 / 1 equals 1. For A, it is 1 / 1 equals 1. For L, it is 2 / 2 equals 1. For O, it is 2 / 2 equals 1. Finally, for N, it is 1 / 1 equals 1. The smallest value among these calculations is 1, which means the maximum number of times we can form the word balloon is 1. Therefore, the output for this example is 1. In the second example, we start with the input string Lundbalksbalpun. First, we count the character frequencies using collections counter, which gives us L4, O5, N2, B2, up1, X1, P1. Next, we use the same frequency requirements for balloon as before, balloon_count equals B1, up1, L2, O2, N1. Now, we calculate the maximum number of times balloon can be formed by dividing the available counts by the required counts for each character. For B, it is 2 / 1 equals 2. For A, it is 1 / 1 equals 1. For L, it is 4 / 2 equals 2. For O, it is 5 / 2 equals 2. For N, it is 2 / 1 equals 2. The smallest value from these calculations is 1, so the output for this example is also 1. In the third example, we use the input string LeetCode. First, we count the character frequencies with collections counter, which gives us L1, E3, T1, C1, O1, D1. The frequency requirements for balloon remain the same, with balloon_count equals B1, up1, L2, O2, N1. To determine how many times balloon can be formed, we divide the available counts by the required counts for each character. For B, it is 0 / 1 equals 0. For A, it is 0 / 1 equals 0. For L, it is 1 / 2 equals 0. For O, it is 1 / 2 equals 0. For N, it is 0 / 1 equals 0. The smallest value across all these calculations is 0, which means it is not possible to form the word balloon even once from the input string. Therefore, the output for this example is 0. The time complexity of our solution is O, N, where N represents the length of the input string text. Let's break this down step by step. First, we count the character frequencies using the counter class from Python's collections module. This involves traversing the input string once, so it takes O, N, time. Next, we define the frequency requirements for the word balloon by creating a dictionary called balloon_count. Since this dictionary only involves a fixed number of assignments for 5 specific characters, its contribution to the time complexity is constant, or O1. Finally, we calculate how many complete instances of balloon can be formed using the min function, which iterates over the 5 keys in balloon_count. Because the size of this dictionary is fixed, this step also takes constant time, or O1. When we combine these steps, the O, N, cost of counting character frequencies dominates the total, making the overall time complexity O, N. Now let's discuss the space complexity, which is O1. Here's why: the char_count object, created by counter, stores the frequency of unique characters in the input string. In the worst-case scenario, where every character in the string is unique, the number of entries in char_count will be proportional to the number of unique characters. For the English alphabet, this maximum is 26, which is constant. Thus, the space required for char_count is 1. Next, the balloon_count dictionary, which stores the frequency requirements for the word balloon, has a fixed size of 5, corresponding to the characters B, A, L, O, and N. This also adds a constant space requirement of 1. Additionally, the min function operates on these 5 keys, requiring only a small, temporary storage for intermediate calculations, which is again 1. Since all these components use constant space regardless of the input size, the overall space complexity remains 1. Let's compare this optimized approach to a naive or brute force method. In a naive solution, we would repeatedly search for and remove the characters needed to form the word balloon. For example, in each iteration, we would locate the characters B, A, L, L, O, and N, which would take N time. Then, removing these characters from the string would also require N time, since strings are immutable in Python and modifying them creates a new copy. This process would repeat for up to n/7 iterations, as balloon contains 7 characters. Combining these steps, the naive approach would have a time complexity of n² in the worst case. In contrast, the optimized solution avoids repeated scanning and manipulation by directly counting character frequencies, reducing the time complexity to n. Both approaches share the same constant space complexity of 1, but the optimized method is significantly faster. Finally, let's analyze the best, average, and worst-case scenarios for the optimized approach. In the best case, the input string consists only of the characters required to form balloon. Even in this scenario, we still need to scan the entire string to count character frequencies, so the time complexity is n. In the average case, the string contains a mix of necessary and unnecessary characters. The counting operation remains linear, so the time complexity is still n. In the worst case, the string consists entirely of characters that are not needed for balloon. Despite this, the counter class will still process every character in the string, so the time complexity does not change, it stays n. Across all cases, the space complexity remains constant at 1, as the memory usage does not depend on the input size. This consistency highlights the robustness of our solution. When solving this problem, there are a few common mistakes to watch out for. One of the biggest pitfalls is not accounting for character frequency mismatches. For example, the word balloon requires 2 L's and 2 O's, so if your input text doesn't provide enough of these letters, it's impossible to form the word. Overlooking this can lead to incorrect results. Another issue is ignoring edge cases. Consider scenarios like input strings that contain none of the letters needed, such as XYZ, or partial matches like below. Failing to address these can cause runtime errors or inaccurate outputs. Additionally, relying on inefficient approaches, such as generating all substrings to check for matches, can lead to n³ complexity, which is impractical for large inputs. Case sensitivity is another area to be mindful of. If the problem requires case-insensitive matching, you need to account for both uppercase and lowercase letters to avoid errors. Lastly, always handle empty or null inputs carefully. Forgetting this validation step could result in crashes or undefined behavior, which is something you definitely want to avoid during an interview or in production code. Now, let's discuss some insights that can help you during interviews. A key strategy is focusing on frequency counts. Problems like this often boil down to analyzing how often each character appears, and tools like hash maps or arrays of size 26 for lowercase letters are efficient for this purpose. It's also important to clarify constraints with your interviewer, such as whether all input strings are guaranteed to be lowercase or if special characters should be ignored. Understanding these details upfront can save you from unnecessary edge case handling. While brute force solutions can demonstrate your initial thought process, it's crucial to optimize quickly. Techniques like sorting or hashing often lead to significant reductions in time complexity. Lastly, make it a habit to test edge cases early in your implementation. Examples like an empty string, repeated patterns like balloon, or strings with no matching characters like XYZ can help you catch logical flaws before investing too much time in debugging. Next, let's look at some related problems that share similar concepts. For instance, LeetCode 383, ransom note, asks you to determine whether one string can be constructed from another using character counts, which is very similar to the frequency analysis in this problem. Another related problem is LeetCode 242, valid anagram, where you validate if two strings are anagrams by comparing their character frequencies. LeetCode 49, group anagrams, takes this a step further by requiring you to categorize strings into groups based on shared character counts. Finally, LeetCode 567, permutation in string, challenges you to detect whether one string is a permutation of another substring. All of these problems emphasize the importance of working efficiently with character frequencies, making them excellent practice if you want to strengthen your skills for this type of problem. Finally, let's explore some alternative approaches to solving the problem. One efficient method is hashmap-based frequency counting. Here, you count the occurrences of each character in both the input text and the target word balloon, then use integer division to determine how many complete words can be formed. This approach has a time complexity of O(n), but requires extra space for the hash map. A slightly more memory-efficient option is using an array of size 26 to track letter frequencies. This method is faster and uses less space but may feel less intuitive if you need to handle non-alphabetic characters. Another technique is a greedy approach with early stopping. In this method, as soon as you detect that any required character is insufficient, you terminate further processing. While efficient, it can be tricky to implement correctly when considering edge cases. Lastly, there's the brute force approach, where you generate all substrings and count valid formations of balloon. While conceptually simple, this method is highly inefficient with a time complexity of O(n cubed, making it unsuitable for larger inputs. Each approach has its trade-offs, and the choice depends on the constraints and context of the problem. Great job! We've covered an efficient way to solve maximum number of balloons using hash maps to track frequencies. Remember to practice similar problems to master this technique. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!